This is my first DPDK summit in Dublin. So for all of you who don't know me, I'm Honnappa. I work at ARM. So when I met the people here, the first question they asked me is, what do you do at ARM? So I took it as, do you even code? So yes, my job is hands-on, developer, submitting patches, reviewing patches in DPDK. That's what I do in ARM. So today, I want to talk about lock-free read-write concurrency in RTE hash. So the agenda I have is, I want to talk a little bit about the current issues that we see in this library, and then I will briefly go over what are the ingredients for lock-free algorithms. It's a topic by itself, but I just want to touch a few things which will help us discuss the design. So I will look at, go over the design that we have for this, and then one of the challenges in a lock-free algorithm is reclaiming the memory. So I have a few ideas over there. We'll discuss that. And then I'll talk a little bit about what's the plan for upstreaming this patch. So current issues. So as Samay mentioned, there was a patch submitted for 1808. There were concerns expressed on the mailing list about concurrency between the reader and the writer. When the reader is reading the key, the writer might take it off from the hash table. So the concerns were valid. They were solved using reader-writer locks, which is a elegant solution in the sense that it's very easy to understand and probably very easy to maintain as well. But one issue that I see with using the reader-writer lock is preemption. So in many of the use cases, the control plane, that's the writer, is on the running on an OS, and he might get preempted while holding the lock, which would block all the readers for an extended duration, and that would result in a heavy drop of packets. So the other thing that I saw is, I'm not an expert on transactional memory, but based on the code that I see in DPDK, sometimes it falls back to using normal reader-writer locks. So what that means is this preemption problem applies for transactional memory as well. I might be wrong, but this is just based on what I see in the code. The second problem is a subtle problem, I would say. Many of the hash add API, it returns the index from the key store, where you have stored the key. But this index is, we say that the application can use this index to refer to its own data. So what that means is the index should not be freed unless the application has said that, hey, I'm not using this index anymore. So today, that's not possible. The RT hash library goes ahead and frees that index. Then another writer can come in and allocate that index again. So this is a subtle problem, and the patch in 1808 does not address this. So then, the performance of the lookups when the writer activity is going on. So this is what I got from a hacked up test code. So what I see here is that when the writer is writing, the hash adds are going on, and you want to do a lookup, the lookup cost is more. So here the orange color is the one with no writers in the background. And when the writers are in the background, the lookup cost increases. So these are some of the issues that we wanted to address. So now, the approach that we took is how can we make this lock-free? So in this context, I just want to go over what are the ingredients for making an algorithm lock-free. So first thing is you need atomic operations. And here, the size of the atomic operation matters, in the sense that like 32-bit atomic operations, they are widely supported on multiple architectures. So choosing a smaller size gives you a guarantee that it's going to work across architectures. That's what I have looked at. I looked for, can I have this on multiple platforms? So I, in fact, experimented with 128-bit atomics, but then I realized that I could do it with 32-bit atomics. The other ingredient we need is memory ordering operations. You could do it with traditional memory barriers or using C11 atomics. And again, the ordering themselves are not enough to have a lock-free algorithm. You need to identify what I call as payload and a guard. So payload is basically the data that you are propagating from the writer thread to the reader threads. And guard is a variable which protects that payload. So basically, you say that, hey, if the payload has the latest, if the guard has the latest data, then your payload is updated. And then you also need to have this synchronized with relationship between the writer and the reader. So probably I have got few diagrams. It will be more clear in the following slides. So every data structure has its own specific challenges, which changes from data structure to data structure. And in this case, we have a specific challenge to solve to make it lock-free. I'll go over that. And the last one is reclaiming the memory. So basically, when the writer deletes an entry, the readers are still referencing that memory or the entry. So you can't really free that memory. So here, I would like to define two terms. One is delete, and the other one is free. So when I say delete, it just removes the reference of that memory or the entry from the data structure. But it does not, it's still valid. That memory is still valid. So free is when you are sure that, hey, readers are done using this, and you can go and add it back to the free pool. So we need mechanisms to identify when all the readers are done using this memory. So I have some thoughts on that, and we'll go over them as well. So now coming to the design, atomic operations, as I said, I experimented with 128-bit atomics, but then I realized maybe 32-bit atomics are better. They are widely supported, and I could change the algorithm using these. So now coming to memory orderings, I think right now I have just used 11 atomics. We really don't want to maintain another version with memory barriers. So as I said, along with memory ordering, we need to identify that payload and the guard. So for the hash table, I have identified two sets of payloads and two sets of guard. I'll show you why we need two sets. If we want to have one set, we need some changes to the existing algorithm. We can discuss that. So the first set is the key itself. Key is the payload, and it need not be an atomic operation. It can be just a series of stores. Then the guard for the key is the data. So that has to be atomic. So both of them are stored in the key store. And next, the payload 2 is the signature and the alternate signature. They are in the bucket entry. And then the guard for the bucket entry is the index of the key in the key store. So here I just want to go over how the memory orderings are happening. So I have represented that in a ladder diagram for us to easily understand. And I have taken a very simple case here to understand this. So there are fairly complicated cases, and I have put them in a backup slide. So whoever is interested, they can take a look at them. So the writer, he stores the key in the key store, and then he does a store release on the data. After that, he stores the signature in the bucket entry, and then he releases the signature by doing a store release on the index. So now the reader comes along. First, he does a load acquire on the index, and then he loads the signature, and then he does a load acquire on the data, and then he loads the key. So the main synchronization that we want to have between the writer and the reader is B and C. But we also have the synchronization between A and D. And as far as the hash add is concerned, A and D synchronization is not needed. So I would like to avoid that. That means it's a less number of memory orderings. We could just live with B and C alone. That is, use the key index as your guard for all these operations. But why do we have two sets? So for that, we need to look at update. So in update, what happens is the writer first does a lookup to identify if that key already exists in the table. If it exists, then he just updates the data. So for an update, what we have is we just have one synchronization between A and C. We don't have the synchronization with the key index. So because of this, I'm forced to use two sets of payload and guard. And I think if we can change the hash update to allocate a new entry and copy the key and data into that, I feel that we can have one set of payload and guard. So I feel with that we could reduce the memory orderings in the hash update as well as hash add. That's something for us to think about. So right now, my patch follows what I have shown here, two sets of payload and guards. But I'm open to changing that to have one set if we all agree that we can change the update. So now moving on, what is the data structure specific challenge in Cuckoo hash? So as Samay mentioned in his earlier slides, hash add can move the entries from their primary location to their alternate locations. But the readers and writers are concurrent now, and there's a chance that the reader might think the entry does not exist in the table, even though it exists. So just to show what that case is, the reader looks up the primary bucket, and the entry is not there because originally the entry existed in the secondary bucket. But before the reader could look up the secondary bucket, the writer comes along and takes that entry from the secondary bucket and moves it to the primary. So now the reader goes and looks at the secondary bucket, but it's not there. So at this point, even though the entry exists in the table, the reader thinks it's not there. So for this, what I did is, basically the writer needs to tell the reader that, hey, while you were looking up, the table had changed, and you need to repeat your lookup. So that's what the writer needs to do. So to do that, I have introduced a global counter. Again, the ladder diagram here is very, very simple for us to understand, but it is fairly complicated. So I have the ladder diagram with all the exact memory orderings in the backup slides. If somebody is interested, please go take a look at that. So in summary, what's going to happen is the reader, before doing the lookup, he reads the global counter. Then the lookup fails in the primary. The writer, before moving the entry from secondary to the primary, he increments the global counter. So he moves the entry. The reader comes along. He looks up the entry in the OK, I have got it wrong. It should be he should have looked up the entry from the secondary, and the lookup fails over there. But at this point, the reader also reads the global counter. And if there is any change in the global counter, it indicates that, hey, the table got changed underneath. And now he's going to repeat that lookup again. He will go back to the primary. He will start looking up, and he finds the entry in the primary table. And he says that, OK, it's a success. So a couple of points on this algorithm. If the entry was present, but it was not moving, then there is no overhead. The lookup will be successful in the first attempt. If the entry is present, but it's moving, then you got to chase that entry. And so the global counter helps it understand that, yes, the entry moved, and you go back and do the lookup again. If the entry is not present, you are looking up an entry which is not there in the table at all. It was not added to the table. Then this lookup routine will loop till these moves stop. But I think that's something that I can improve. This global counter can be changed to a per bucket counter, and I can improve the performance on that. So now the last part, reclaiming the memory. So here, I want to talk about this thread quiescent state. In short, I just call it as TQS. So TQS is a place in the code where thread does not hold any reference to shared memory. So basically, I have shown here the reader threads, and then each thread is nothing but a while one loop. So in this in this picture, the blue ones are the quiescent states, where the thread does not hold any reference to the shared data. But this quiescent state is completely application defined. So in this case, those are the quiescent states. And then one application might say that for the data structure D1, the rest of them are quiescent states. And then so D1, D2, D3 are basically critical sections where the thread is having a reference to those respective data structures. So some applications might say that, hey, the beginning and the end of the while loops are quiescent states, and anything in between is a critical section. So basically, it groups all the data structures and says that, hey, this is my critical section. So it is up to the application as to how it defines its quiescent state. So now coming to the delete and free. So what do we need to do? So at this point, on the time scale, you delete the entry, but the threads are still having a reference to that entry in the D2 data structure. So we cannot free that entry or free that memory at this point. So when can we free it? So, yes, as I said, at delete, you can remove the reference to that entry, but you can't free it. And we can also see that once the delete happens, other threads can go into that data structure, but they will not find a reference to that deleted entry. So when can we free the memory associated with that entry? You can free it only after every thread has gone through one set of quiescent state. So we can't free it in that time gap between delete and the end of the quiescent state. So what I would like to do is I would like to introduce what I call as a RTE_TQS library. So what it will do is it will provide the ability to check if a given set of readers are done referencing an entry or a memory location. So the goal for this library from my side are provide flexibility. As I said, the definition of quiescent state is left to the application. So it could be over a single data structure, or it could say, hey, I want to have over a group of data structure. It is left to the application. And I would like to give the ability to check the quiescent state for all our given set of readers. You should be able to check the quiescent state synchronously, as in you delete an entry, and then you wait at that point till the quiescent state is over to free it. And then I also want to provide a facility wherein quiescent state can be checked at a later point. You trigger that quiescent state querying to the readers, but you come back at a later point and check if they have really done or not. So these are some of the goals I have set for this. So at this point, I have this set of APIs. I think in the interest of time, I will probably skip this. You can go through what these APIs are. Yeah, that's it. And plans for upstreaming, I have the lock-free read-write concurrency patch ready. I would like to upstream it probably beginning of next week. And then as far as the TQS library is concerned, it's at a high-level design API definition done. But I still need to do coding and testing, and I target to do that in the next quarter. So yeah, that's it from my side.